We have seen how to grow the buffer. Now let's ask the big question. Why do we double the size, and why does this make append cheap on average? Let's look at the growth strategy and its cost. Look at this picture. We start with a seed block of capacity 1. Each resize doubles the capacity. The amber part is the old contents we copy over. The blue part is fresh spare room. Let's reveal the resizes one at a time. First resize. Capacity grows from 1 to 2. We copy one element, the old contents. Second resize. Capacity grows from 2 to 4. Now we copy 2 elements. Third resize. Capacity grows from 4 to 8. We copy 4 elements. Fourth resize. Capacity grows from 8 to 16. We copy 8 elements. Each step copies more, but there are far fewer steps. Count the copies down the page. 1, then 2, then 4, then 8. Each one is double the last. This is a geometric series, and it sums to less than 2 times, and that is a small total. Now compare the other idea. If we grow by a constant, say +1 each time, then every single append copies the whole array. That is big O of n squared in total. Multiplying, not adding, is what keeps the work small. That is why a vector doubles. Let's try a quick check. A vector doubles 1, 2, 4, 8, 16. On the resize that grows capacity from 8 to 16, how many elements are copied, and which append triggers it? Think for a moment. Now the answer. 8 elements are copied because the block was full at size 8. The 9th append triggers it. That is the append that finds size equal to capacity, both equal to 8. Let's add up the work. Take n to be a power of 2, so the array grows 1, 2, 4, and so on up to n copies happen only on a resize. The resizes fire on appends 1, 2, 3, 5, 9, 17, and so on. Each copy moves the current size. Add up those copies. 1 plus 2 plus 4, and so on up to n over 2. That whole sum is n minus 1, which is less than n. Now add the cheap end rights. There is 1 right per append, so that is n more units. The whole run of n appends does less than 2 times n units of work. Divide that by n, and the cost per append is big, O of 1 on average. Let's be clear about the word amortized. It means the average cost per operation over a whole sequence. It is not the cost of one call. A single append can be big O of n on a resize, but any sequence of n appends is big O of n in total. So each one is big, O of 1 on average. Watch out for one thing. Amortized big O of 1 does not mean every append is big O of 1. The resizes, on appends 1, 2, 3, 5, 9, and so on, each cost big O of the current size. They get rarer and rarer, so the average over the whole run is constant, but a resize append still spikes. Let's check your understanding. In your own words, a single append can cost big O of n, yet we call append big O of 1 amortized. How do these two ideas fit together? Think for a moment. Now the answer. The rare big O of n resize copies at most n elements, but it only happens after n over 2 cheap appends since the last one. Each cheap append prepays about 2 units, so the total work over any n appends is under 2 times, and that is a constant average, even though one call spikes. Let's read this chart. The bottom axis is the append number from 1 to 16. The height of each bar is the cost of that append. The cost is 1 right plus the elements copied on that step. The amber bars are the resizes. Each amber bar is an append that triggered a resize. They fall on appends 1, 2, 3, 5, and 9. They spike up high and they get taller as the array grows. The first one allocates but copies nothing. The blue bars are short. Each blue bar is a plain cheap write with no copy. Its cost is just 1. Notice there are many blue bars between the amber spikes. Now the green dashed line. It is not a running average. It marks the amortized bound, about 2. Even though a few bars spike very high, the spikes are rare. So the cost per append stays near this flat line. Let's read the plot in words. Each bar is the cost of 1 append, 1 write plus any copies. The tall spikes are the resizes at appends 1, 2, 3, 5, and 9. They grow taller, but they get rarer. The dashed line is the amortized bound, about 2. This is the whole idea in one picture. The spikes get taller, but they get rarer even faster. So the average stays flat and low. That is why append is big, O of 1 amortized.